Okay, in this video, we will do examples of normal approximation for binomial random variables. I will try to do step by step such that you see all the steps I explained in another video for approximating a binomial random variable using a normal random variable. Okay, so let's start with the first probability. This is probability of B binomial 100 and 0.5 less than equal to 60. The first step to complete always is that identify and find the normal random variable, which is a good approximation for B and P. And we know that normal random variable y, which has, remember, normal random variables have two components, two things that you have to fix. One is mean and one is sigma, but the one which approximates B and P has the same mean as that B and P. So NP in this case 100 times 0.5. This is equal to 50. And same sigma, so n square root of np1 minus p here gives us 100 0.5 times 0.5, and that's root 25, which is 5. This y is a good approximation for B100 and 0.5. Yes, that's a step one. Then step two is that we turn B probability to continuous Y probability. So if we start with probability of B100 and 0.5 less than equal to 60, this can be turned into an interval for Y. But how do we find that y? This is what you need to see here. For binomial, we have these values, 60, including 60, then 59, and then 58, and so on. To go into continuous, we taken each point halfway up, halfway down, but halfway up here is 1 over 2 or 0.5. So the largest value we are allowed to give to y is 60 plus 0.5, and then it will be an interval all the way down. So it will be 60 plus 1 over 2, which is 60.5. Okay, that's step two, but means that we approximated probability using the continuous random variable. Step three is that you turn y to standard normal random variable. In other words, we know that y minus mu over sigma is the standard normal random variable. So whenever you see, or you can generate y minus 50 over 5, you can replace it by z. To do that, we do subtract 50 from both sides. Oops. And then divide both sides by probability. Divide both sides by 5. This is 10.5 over 5. And you see that y minus 50 over 5 is z. And then this is 2.1. So now we are in z variable probability. And here what is important to note that while z and y are continuous, we can include or not, but include equality or not. All being said, to find the probability, we need to use the table, the z table. Use the table. So in this case, let me import the table here somewhere. Okay, I'll do it here. Normal, that's nice. Yes, okay. And this is 2.1. 2.1 is somewhere here. Yes, 2.1. And then that means that the second decimal is 0. So we have the 0.9821, and that's the final 0.9821. This last step, you may see that it can have several steps. In this case, it was just easy, and we were able to compute and finish part 1, which gave us 0.9821. Okay, that's the first example. How about the second one? So let me bring it down here. So 2, we are trying to find probability of B100 0.5 less than 60. Very nice. Well, the first step of what is y normal random variable that approximates is exactly same as before. So we already found that step. So I will start from step 2, which turning b to y, b probability to y probability. Okay. Before I go, something that you need to be very, oh, this is 41. Something that you have to be very careful here is that, well, this includes 41, but this guy doesn't include 63. So we have to be careful. It means that the discrete random variable will go up to the number which is before 63. So in other words, this probability is same thing as B100 0.5 less than equal to 62. Okay, now we can turn this to y. Y, remember that if we have continuous, the discrete from 41 to 62, we go halfway up, halfway down on each one of these guys. Halfway up, halfway down, and then everything in between. And what will remain will be from halfway down of 41, which is 40.5, up to halfway up of 62, which is 62.5. So that is the y interval for us. That means we can replace this by y being bigger than 40.5, less than 62.5. And that's, again, you can put either equalities here or not, doesn't matter, because this is continuous and variable and you don't need to be worried about equality or not. Okay, that's it. Well, that's step 2. Step 3 is we turn this y to z, to standard normal. So y to z, and again y minus 50 over 5 will be the standard normal random variable. So we need to do 40.5 minus 50, y minus 50, 62.5 minus 50, and this is probability of, this is negative 9.5 divided by 5, y minus 50 divided by 5, and this part here is 12.5 divided by 5. This middle piece is z, so I have probability of z being less than bigger than negative 9.5. This is, well, this is just an easy computation. It will be negative 1.9, and z less than 12.5 is 2.5. Very nice. Now we have Z, and then the last step is use the properties of step 4. Use the properties of Z and the table to evaluate. Use the table. Let me just write. Use the table. Okay, so it means that we write first probability of Z less than 2.5 minus probability of Z less than the smaller value. But we see that the smaller value is negative, so we can turn it to positive by doing this, flipping the inequality. And then Z is bigger than some positive, so we can turn it to negative to less than by 1 minus this thing. So this means that we have probability of Z less than 2.5 plus probability of Z less than 1.9 and then minus 1. Okay, so we turn that probability into two probabilities from the table. Let me bring the table down such that I can use it. Okay, here. And what we have here is 2.5. 2.5 is here, and that goes, the second component is, the second decimal is 0, so that gives us 0.9938 plus 1.9 is somewhere here. Yes, 9713. 0.9713 minus 1. And well, we have to add these two. 1, then 1 goes there. 1 and 3, 4. And then we have 5, 7, and 9 is 16. Then 1 goes there. 9 and 9 is 18. We have 9 there, 1. And then minus 1 gives us 0.9651. Again, following all the steps, we were able to compute the probability of B100 0.5 being between 41 and less than 63 is equal to 0.9650.